Now in this lecture we'll answer on two questions. In the first question we find out the size of this angle x, and in the second question we find out the area of this green shape. So we start with the first question. In the drawing we have a quarter circle. AOB is a quarter circle. This is an angle AOB, that is a right angle. Angle APQ is also a right angle, and we also know that AP equals to PQ. Again, our test is to find out the size of angle PQB is equal to x. We have to find out the value of angle x. So first of all, we will complete the quarter circle to a semicircle. And we will find this point as point M. So actually, AM is the diameter of the semicircle according to our construction. So right now, AM is the diameter of the semicircle. AM is a diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the areas must be equal to 180 degrees according to Rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is a right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will extend line segment PQ by straight line until it touches the semicircle. But the question is, where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at this point L. So according to our assumption, we have peripheral angle APL that is equal to 90 degrees in size according to what is given as the question, and peripheral angle APL subtend on chord AL. Again, peripheral angle APL definitely subtend on chord AL. But the problem is that chord AL is not the diameter of the semicircle because it doesn't pass from point O, that is the center of the semicircle. And we know that any only chord that passes through the center of the semicircle can be the diameter of the semicircle. Therefore, chord AL is definitely not the diameter of the semicircle, and therefore we have contradiction to rule 5. So please click on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the drawing you have a circle. This is peripheral angle AOB that is equal to 90 degrees in its size, and therefore it must subtend on the diameter of the circle, and indeed peripheral AOB subtend on AB, that is the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. And therefore we have here peripheral angle APL that is equal to 90 degrees in its size, and according to rule 5, peripheral angle APL must subtend on the diameter of the semicircle. But peripheral angle APL subtend on AL, that is definitely not the diameter of the semicircle because it doesn't pass from point O, that is the center of the semicircle. So we have a contradiction to rule 5. Okay, therefore, due to the contradiction to rule 5, the extended line segment PQ cannot touch the semicircle at point L. In the next step, we will assume that the extended line segment PQ will touch the circle at this point H. But again, we will assume that the extended line segment PQ will touch the circle at this point H. So according to our assumption, we have peripheral angle APH that equals to 90 degrees in its size according to what is given us in the question, and peripheral angle APH definitely subtend on chord AH. Again, peripheral angle APH subtend on chord AH. Again, we have contradiction to rule 5 because AH is definitely not the diameter of the semicircle because AH doesn't pass through point O, that is the center of the semicircle. But according to rule 5, peripheral angle APH must subtend on the diameter of the semicircle, but AH is not the diameter of the semicircle. So due to the contradiction to rule 5, we must conclude that the extended line segment PQ cannot touch the circle at point H. And therefore, we will conclude that the extended line segment PQ will touch the semicircle at point M. Again, the extended line segment PQ will touch the semicircle at point M and not in any other point. Now we don't have contradiction to rule 5 anymore because we have peripheral angle APM that is equal to 90 degrees in its size, and indeed it subtends on AM, that is the diameter of the semicircle, exactly according to rule 5. Okay. In the next step, we will join points A and Q together by straight line. By joining points A and Q, created the right and associated triangle, triangle APQ. Triangle APQ is a right angle because angle APQ is a right angle, and triangle APQ is an associated triangle because side AP equals to side PQ. And we have the rule that in front of equal sides in the triangle there are equal angles. So if we relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the sides of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. And we also know that the sum of the angles in any triangle is equal to 180 degrees. It is equal to it is true in any triangle, therefore it must be true in the right hand associated triangle, triangle APQ. So which angles we have in the right hand associated triangle, triangle APQ? We have this angle that is a right angle. Alpha plus alpha is 2 alpha. So 90 degrees plus 2 alpha must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation. Here we subtract 90 degrees from this equation. 90 degrees plus 2 alpha equals to 180 degrees. We subtract 90 degrees from this equation, and we get that 180 degrees minus 90 degrees is 90 degrees. So if you found out that 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So this is the missing angle alpha, that is equal to 45 degrees in size. And this is also the missing angle alpha, that is equal to 45 degrees in size. In the next step, we will prove that those two right triangles can go into each other according to side angle side rule. That is to say, we prove that the right upper triangle, triangle AQO, can go into the right lower triangle, triangle OQM according to side angle side rule. So it is now we have to prove that the right upper triangle, triangle AOQ congruent to the right lower triangle, triangle OQM. So why those two right triangles can go into each other? First of all, AO equals to OM, the above the radii of the semicircle, therefore they are equal to each other. So if we define the radius of this semicircle as R, then AO equals to R and OM equals to R. So write it down. AO equals to OM. Repeat again. Thus we found out that side AO of the right triangle AOQ equals to side OM of the right triangle OQM, the above the radii of the circle, therefore they are equal to each other. In addition, those two angles they are both equal to 90 degrees and therefore they are equal to each other. So this is angle AOQ in the right upper triangle AOQ, and it is equals to this angle, this is actually angle MOQ in the right lower triangle, triangle MOQ. This again, angle AOQ in the right triangle AOQ is equals to angle MOQ in the right triangle OQM. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side OQ, that is a common side that belongs to both triangles. So you can write down that OQ equals to itself. It's a common side that belongs to both triangles. Because again, I'm sure you found out that side OQ equals to itself is a common side that belongs to both triangles. So if you prove that the right upper triangle AOQ can go into the right lower triangle OQM according to side angle side rule. So write it down. We shall prove that the right upper triangle AOQ congruent, this is the sign of congruent, to the right lower triangle, triangle OQM according to side angle side rule. That is to say, we shall prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ corresponding equal to those two sides and the angle that is included between those two sides in the right lower triangle OQM. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive the side AQ of that triangle AQO is equal to side QM of the right lower triangle OQM. Write it down. We derive that AQ equals to QM. AQ equals to QM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their length. So if you found out that AQ equals to QM, so if you relate to the big associated triangle AQM, we have the rule that states that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in the associated triangle AQM, the big associated triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. In the next step, I will present to you a new rule and we will implement the new rule in our drawings. The new rule is rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. I repeat again, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. In the drawing we have triangle ABC that would be a triangle. Those three angles alpha, beta and gamma are defined as an interior angles because they are located inside triangle ABC, while this is angle ACF that is defined as angle E. Angle E is an exterior angle because it is located outside triangle ABC. And according to this rule 8, the size of the exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. This is the interior angle gamma that is definitely adjacent to angle E. The two other interior angles that are not adjacent to angle E are those two angles, alpha and beta. So according to rule 8, the size of the interior angle E is equal to alpha plus beta. So we can implement rule 8 in our drawing. One, because in our drawing, if we relate to the big associated triangle AQM, those three angles are defined as an interior angles. This is angle AQP that is defined an exterior angle because it is located outside the associated triangle AQM. And according to rule 8, the size of the exterior angle AQP is equal to the sum of the two interior angles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other angles that are not adjacent to angle AQP are those two angles. So according to rule 8, the size of the exterior angle AQP is equal to beta plus beta. So I'll write it down. So according to rule 8, if we relate to the big associated triangle AQM, the size of the exterior angle AQP is equal to the sum of the two interior angles that are not adjacent to it. That is to say, it is beta plus beta. Beta plus beta is 2 beta, so We should find out that the size of the external AQP, the size of this external AQP is equal to 2 beta. But we already found out that the size of the external AQP is equal to 45 degrees. So we can substitute again AQP by 45 degrees. And we get that 45 degrees equals to 2 beta. Here we divide this equation by 2. And finally we get that the size of angle beta is equal to 45 degrees over 2, that is 22.5 degrees. So if we found out that this is angle beta, that's equal to 22.5 degrees in its size, and this is also angle beta, that is equal to 22.5 degrees in its size. In the next step, we'll focus on the right lower triangle, triangle OQM. In the right lower triangle, triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have the right lower triangle and triangle OQM? We have this angle that is a right angle, plus this is angle beta that is equal to 22.5 degrees in its size, plus the size of this missing angle, angle OQM. In total, the sum of those three angles must be equal to 180 degrees. The sum of those three angles must be equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that 22.5 degrees plus the size of the missing angle, angle OQM. In total, they must be equal to 180 degrees minus 90 degrees is 90 degrees. So if we found out that 22.5 degrees plus the missing angle OQM, in total they must be equal to 90 degrees. Here we subtract 22.5 degrees from this equation, and we get that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees, that is 67.5 degrees. So if we found out that the size of this missing angle OQM is equal to 67.5 degrees. So write it down. Here we will implement the rule that says that vertex angles are equal to each other. So, again, we will implement on our domain the rule that says that vertex angles are equal to each other. Those two angles, alpha and beta, are defined as vertex angles and they are equal to each other in their sizes. So we can write down that alpha equals to beta. Likewise, those two angles are also defined as vertex angles. So those two angles are also equal to each other and their sizes. So angle 1 equals to angle 2 in its size. So I can implement the new rule in our drawing. Why? Because in our drawing, we have those two angles that are defined as vertex angles and they're equal to each other and their sizes. This is to say angle x equals to 67.5 degrees in its size. Angle x equals to 67.5 degrees in its size. And that is actually the answer to our question. We actually found out that the size of this missing angle PQB is equals to x is 67.5 degrees. So we finished with the first question. In the next step, I will present to you the second question and we will solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have a semicircle. PQ is the diameter of this semicircle. That is equal to 10 units in itself. Therefore, the radius must be equal to 5. So write it down. The radius of this semicircle is equal to 5 units in its length. In addition, we have inside this semicircle the big square ABCD and the small square MEFC. Again, our task is to find out the area of this green shape. So first of all, we will define the center of this semicircle. This point is point O. And we will join points O and A together by a straight line. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle that is equal to 5 units in its length. The radius of the semicircle equals to 5. In the next step, we join points O and D together by a straight line. OE is of course the radius of this semicircle that is equal to 5 units in its length. MEFC is a square, therefore this angle must be equal to 90 degrees in its size. Likewise, ABCD is a square, and therefore this angle must be also equal to 90 degrees in its size. In the next step, we will define the length of one side of the big square ABCD is A. So AB equals to A. It is equals to AD equals to DC equals to CB is equals to A. Likewise, we define one side of the small square MEFC as B. So EF equals to B, CF also equals to B, CM equals to ME equals to B. We define the length of the short line segment OC as X. So what is the length? What is the length of the short line segment BO? BO equals to BC minus OC. So if it write it down, BO equals to BC minus OC. So BO equals to BC. BC is A minus OC. OC is X. So in total, BO equals to A minus X units in its length. BO equals to A minus X. And OC or OF equals to X plus B. Okay. So in the next step, I'll copy the right triangle ABO in a new question. We will implement on this right triangle ABO the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle ABO that is coming from the original drawing. This right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So I will write it down. This will be equation 1. AO squared, that is the square of the hypotenuse, is equal to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25. And it is equals to AB squared. AB is 8, therefore AB squared is A squared plus BC squared. BC is A minus X, therefore BC squared is A minus X squared. So in total, according to equation 1, we actually found out that 25 equals to A squared plus A minus X squared. Likewise, I'll copy the right triangle OFE in a new page and we will implement on this right triangle OEF the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. Side OF of the right triangle OEF equals to X plus B in total. Okay. So actually, this is the right triangle OEF that is according to the original drawing. This right triangle OEF, according to the Pythagoras theorem, OE squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. So I write it down. This will be equation 2. According to equation 2, OE squared, that is the square of the hypotenuse, is equal to EF squared plus OF squared. The hypotenuse OE equals to 5 units in step, therefore OE squared is 5 squared, that is 25. And it is equals to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF is X plus B, therefore OF squared is X plus B squared. So in total, according to equation 2, we actually found out that 25 equals to B squared plus X plus B squared. This is according to equation 2, and according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. Therefore, we get equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. But again, according to equation 3, 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to a squared plus a minus x squared. And it must be equal to 25 according to equation 2. 25 according to equation 2 equals to b squared plus x plus b squared. So here we will open the brackets on both sides of this equation, equation 3, and we get that according to equation 3, a squared plus a minus x squared. A minus x squared equals to a squared plus x squared plus 2 times a times x, and it is equals to b squared plus x plus b squared. X plus b squared equals to x squared plus b squared plus 2 times x times b. Here we have x squared on both sides of this equation, so x squared will get cancelled. After we cancel x squared, inside of this equation 3 we're left with a squared plus a squared, that is 2a squared minus 2ax. While on the other side of this equation 3 we're left with b squared plus b squared, that is 2b squared plus 2xb. So total according to equation 3 we actually found out that 2a squared minus 2ax equals to 2b squared plus 2xb. Here we divide this equation 3 by 2, and we get that according to equation 3, 2a squared over 2 is a squared, and it is minus 2ax over 2 is ax, minus 2ax over 2 is minus ax, and it is equals to 2b squared over 2 is b squared, and 2xb over 2 is xb. So in total according to equation 3 we actually found out that a squared minus ax equals to b squared plus xb. Here we will add ax to this equation 3, and get that according to equation 3, a squared equals to ax plus bx plus b squared. So here we subtract b squared from this equation 3, and get that according to equation 3, a squared minus b squared equals to ax plus bx. So here we take x as a common factor from those two expressions, so inside the brackets we left with a plus b. So in total, according to equation 3, we actually found out that a squared minus b squared equals to x times a. A squared minus b squared equals to x times a plus b. We have the famous algebraic identity that states that a squared minus b squared equals to a plus b times a minus b, and it is equals to x times a plus b. A is the length of one side of the big square ABCD, and B is the length of one side of the small square MEFC. So A and B as a length, there must be a positive number, and when you add two positive numbers to each other, the result must be a positive number. Therefore, A plus B must be a positive number. Therefore, we can divide this equation 3 by A plus B, because A plus B must be a positive number. It can never be equal to 0. So it is allowable to divide this equation 3 by A plus B. So we divide the equation 3 by A plus B, and we get that here, in this side of equation 3, A plus B will get cancelled, and we're left only with A minus B. And the other side of this equation 3, A plus B also gets cancelled, and we're left only with X. So total according to equation 3, we actually found out that A minus B equals to X. Here we will add B to this equation 3, and finally get that according to equation 3, A equals to X plus B. Here we subtract x from this equation 3, and finally get that according to equation 3, a minus x equals to b. Here we square both sides of this equation 3, and we get that according to equation 3, a minus x squared equals to b squared. But again, according to equation 3, we actually found out that a minus x squared equals to b squared. Our task is to find out the area of this green shape. So again, our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total, it is equal to the area of the big semicircle as the area of the big square ABCD minus the area of the small square MEFC. Repeat again. Actually found out that the area of this green shape is equal to the area of the semicircle minus the area of the big square BCD minus the area of the small square. The area of the semicircle equals to the area of the circle over 2. That is to say, it is equal to pi r square over 2. But the radius of this semicircle is 5. Radius equals to 5. So pi r square over 2 is pi times 5 square over 2, that is 25 pi over 2. So in total, we found out the area of this big semicircle is equal to 25 pi over 2 square units in its size, minus the area of the big square ABCD. One side of the big square ABCD is equal to a unit in its length, therefore the area of the big square is a square, that is, therefore it is minus a square. One side of the small square is equal to b units in its length, therefore the area of the small square is b square, so it is minus b square. So in total, we actually found out that the area of the green shape equals to 25 pi minus a square minus b square. So it is actually equals to 25 pi over 2, that is the area of the semicircle, minus a square minus b square. So here we take minus 1 as a common factor from those two expressions, so inside the brackets we left with a square plus b square. So in total we should found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. According to equation 1, we have already found out that 25 equals to a square plus a minus x square. Repeat again, according to equation 1, we already found out that 25 equals to a square plus a minus x square. And according to equation 3, we have already found out that a minus x square equals to b square. A minus x square equals to b square. This is according to equation 3. So we can actually substitute a minus x square in equation 1 by b square from equation 3. Why? Because a minus x square equals to b square. We do it now, we get that according to equation 1, 25 equals to a square plus a minus x square. And a minus x square according to equation 3 is b square. So according to equation 1, we actually found out that a square plus b square equals to 25. A a squared plus b squared equals to 25 according to equation 1. Therefore, we can substitute a squared plus b squared here by 25. We do it now, then get that the area of the green shape in total equals to 25 pi over 2 minus a squared plus b squared, that is 25 according to equation 1. So in total, we should find out the area that we are looking for in this equation, that is the area of the green shape, is equal to either 25 pi over 2 minus 25 square units in its size, or in terms of numbers, the value of this expression is equal to 14.27 square units in its size. Okay, again, we should find out that the area that we are looking for in this question, that is the area of the green shape, it is equal to either 25 pi over 2 minus 25 square units in its size, or in terms of numbers, the area of this green shape equals to 14.27 square units in its size. So we finished with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out. In the first question, our task was to find out the size of this angle PQB is equal to x. We have to find out the value of angle x. So in the moment, we have a quarter circle. AOB is a quarter circle. This is angle AOB, that is a right angle. This is angle APQ, that is also a right angle. In addition, we know also that AP equals to PQ. Again, our task is to find out the size of angle PQB, it is equal to x. We have to find out the value of angle x. So in the first step, we completed the quarter circle to a semicircle. And therefore, AM must be the diameter of the semicircle. Again, AM is the diameter of the semicircle. Again, AM is the diameter of the semicircle according to our construction. Okay, AM is the diameter of the semicircle. So AM is a diameter, it is absolutely a straight line. AM is a straight line, so if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to the rule that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we extended the straight line PQ by straight line until it touches the semicircle. The question is, well, the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at this point, point L. And therefore, according to our assumption, we have peripheral angle APL that is equal to 90 degrees in its size according to what is given in the question, and peripheral angle APL subtend on chord AL. Again, peripheral angle APL subtend on chord AL. But the problem is that AL is definitely not the diameter of the semicircle, because AL doesn't pass for the center of the semicircle at this point O. And we know that only a chord that passes through the center of the semicircle can be the diameter of the semicircle. And because of the fact that AL doesn't pass through the center of the semicircle, AL is not the diameter of the semicircle. So it is a contradiction to rule 5, because we have peripheral angle APL that is equal to 90 degrees in size. So according to rule 5, peripheral angle APL must subtend on the diameter of the semicircle, but peripheral angle APL subtend on AL that is not the diameter of the semicircle. Therefore, due to the contradiction to rule 5, we have to conclude that the extended line segment PQ will not touch the semicircle at point L. In the next step, we assume that the extended line segment PQ will touch the semicircle at this point H. We touch the circle at this point H. So according to our assumption, we have peripheral angle APH that is equal to 90 degrees in size according to what is given in the question, and peripheral angle APH definitely subtend on chord AH. Again, peripheral APH subtend on chord AH. But the problem is that AH is definitely not the diameter of the semicircle because it doesn't pass through point O, that is the center of the semicircle. So due to the contradiction to Rule 5, we must conclude that the extended diameter PQ will not touch the circle at point H. So therefore, we must conclude that the extended line segment PQ will touch the semicircle at point M and not in any other point. Now we will not have contradiction to Rule 5 because we have here peripheral angle APM that is equal to 90 degrees in its size, and indeed peripheral angle APM subtend on AM, that is the diameter of the semicircle according to our construction. Okay. In the next step, we join points A and Q together by straight line. By joining points A and Q, we create the right and associated triangle, triangle APQ. In the right and associated triangle, we have the rule that says that in front of equal sides in the triangle, there are equal angles. So if we relate to the right and associated triangle, triangle APQ, in front of those two equal sides, those two sides are equal to each other according to what is given as the question. AP equals to PQ. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right and associated triangle APQ? We have 90 degrees plus alpha, this is 2 alpha. In total, it must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So 90 degrees minus 1 alpha equals to 180 degrees. If we subtract 90 degrees from this equation, we found out that 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. If we divided this equation by 2, we found out that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So this is the missing angle alpha that is equal to 45 degrees in size, and this is also the missing angle alpha that is equal to 45 degrees in its size. In the next step, we prove that those two right angles can go into each other according to side angle side rule. That is to say, we prove that the right upper triangle AQO can go into the right lower triangle OMQ according to side angle side rule. So why those two right angles can go into each other? First of all, AO equals to OM, they're both the radius of the semicircle, therefore they are equal to each other. Okay. In addition, those two angles, they are both right angles, and therefore they are equal to each other. And finally, OQ is a common side that belongs to both triangles, so we can write down that OQ equals to itself is a common side that belongs to both triangles. So in total, we should find out that those two right triangles can go into each other according to side angle side rule. And then again, we should find out that the upper right triangle AOQ can go in, this is the side of congruent to the lower right triangle OQM according to side angle side rule. This is to say, we should prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides in the right lower triangle OQM. And therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that OQ equals to QM. That AQ equals to QM. Side AQ of the right upper triangle AQM, side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM. AQ equals to QM according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. We have the rule that in front of equal sides in a triangle there are equal angles. So if we relate to the big associated triangle, triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. The next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is Rule 8. So if we quickly Rule 8, according to Rule 8, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. Again, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. In the drawing, we have triangle ABC that could be any triangle. Those three angles alpha, beta, and gamma are defined as interangles because they are located inside triangle ABC. While this is angle ACB that is located outside triangle ABC, and therefore it is defined as an exoangle. Define the exoangle ACF as E. So what is the size of the exoangle angle E? According to this rule 8, the size of the exoangle E is equal to the sum of the two interangles that are not adjacent to it. This is the interangle gamma that is definitely adjacent to angle E. The two other interangles that are not adjacent to it are those two angles alpha and beta. And therefore, according to this rule 8, the size of the exoangle E is equal to alpha plus beta. Okay, so we can implement rule 8 in our drawing. Why? Because in our drawing, if we relate to the big associated triangle AQM, those three angles are defined as triangles. This is angle AQP that is defined as an exoangle because it is located outside the associated triangle AQM. And according to rule 8, the size of the exoangle AQP of the associated triangle AQM, the size of the exoangle AQP is equal to the sum of the two rectangles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other angles that are not adjacent to angle AQP are those two angles. Therefore, according to rule 8, the size of the exoangle AQP is equal to beta plus beta. This again, according to rule 8, if we relate to the big associated triangle AQM, according to rule 8, the size of the exoangle AQP equals to the sum of the two interangles that are not adjacent to it. That is to say, it is beta plus beta, that is 2 beta. So the size of the exoangle AQP is equal to 2 beta. But we have only found out that the size of the exoangle AQP is equal to 45 degrees. So we can substitute angle AQP by 45 degrees. So 45 degrees equals to 2 beta. Here we divided the equation by 2 and can find out that beta equals to 45 degrees over 2 is 22.5 degrees. So this is angle beta is equal to 22.5 degrees in size, and this is also angle beta that is equal to 22.5 degrees in its size. In the next step, we focus on the right lower triangle OQM. In the right lower triangle OQM, the sum of the angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right lower triangle OQM? This angle that is right angle plus this angle beta that is equal to 22.5 degrees in size, plus this missing angle OQM. In total, the sum of those three angles must be equal to 180 degrees. Repeat again, in the right lower triangle OQM, 90 degrees plus 22.5 degrees, plus the size of this missing angle OQM, in total must be equal to 180 degrees. Here we subtract the 90 degrees from this equation, and finally found out that 180 degrees minus 20 degrees is 90 degrees, so 90 degrees equals to 22.5 degrees plus the size of the missing angle OQM. Here we subtract 22.5 degrees from this equation, and finally found out that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is 67.5 degrees. So if you found out that the size of this missing angle OQM is equal to 67.5 degrees. In the next step, we implemented the rule that vertex angles are equal to each other in our drawing. Those two angles are defined as vertex angles and are equal to each other. That is to say, alpha equals to beta. Those two angles are also defined as vertex angles and are equal to each other. That is to say, angle 1 equals to angle 2. So you can actually implement this rule in our drawing, because in our drawing we have those two angles that are defined as vertex, those two angles that are defined as vertex angles, and they are equal to each other. That is to say, angle x equals to 67.5 degrees in its size. If we found out that the angle that we are looking for in this equation, that is angle s, and angle x is equal to 67.5 degrees in its size. And again, if we found out that the size of angle PQB that is equal to x is equal to 67.5 degrees in its size. So we finish with the first question. In the next step, I presented to you the second question. We solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the domain we have a semicircle PQ is the diameter of this semicircle that is equal to 10 units in itself, therefore the radius must be equal to 5. In addition, we know that inside this semicircle we have the big square ABCD and we have the small square MEFC. Again, our task is to find out the area of this ring shape. First of all, we define the center of this semicircle. This point is point O. We join points O and A together by a straight line. OA is the radius of the semicircle, that is 5. We join points O and E together by a straight line. O is also the radius of this semicircle, that is equal to 5. ABCD is a square, therefore this angle must be equal to 90 degrees in its size. Likewise, MEFC is also a square, and therefore this angle must be equal to 90 degrees in its size. In the next step, we define the length of one side of square ABCD as A. Therefore, AB equals to BC equals to CD equals to DA equals to A. Likewise, we define one side of the small square MEFC as B. Therefore, MC equals to C, F equals to FE equals to EF equals to B. We define the length of this short line segment OC as X. So what is the length of OB? OB equals to BC minus OC. Again, OBO equals to BC minus OC. So BO equals to BC, that is A, minus OC, that is X. So in total, OC equals to A minus X units in its length. In the next step, I copied the right triangle AOB in a new page and we implemented the Pythagoras theorem on this right triangle AOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle AOB that according to the original domain. In this right triangle AOB, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, this is 25, and this is equals to AB squared. AB is 8, therefore AB squared is A squared plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So in total, according to equation 1, we actually found out that 25 equals to A squared plus A minus X squared. Likewise, I copied the right triangle OEF in a new page and implemented the Pythagoras theorem on this right triangle OEF. Side OF equals to X plus B. EF equals to B, and OE is also the radius of this semicircle, that is equals to 5 units in its length. So this is the right triangle OEF that I copied from the original domain. Here by PT is the provision for Pythagoras theorem. According to the Pythagoras theorem, this right triangle OEF, OE squared, that is the square of the hypotenuse, equals to EF squared plus OF squared. OE is 5, therefore OE squared is 5 squared, that is 25, and this is equals to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF is X plus B, therefore OF squared is X plus B squared. So in total, according to the equation 2, we found out that 25 equals to B squared plus X plus B squared. This is according to equation 2, while according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. Therefore, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. Okay, again, according to equation 3, equation 3 says that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A squared plus A minus X squared. And it is equals to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. Here we open the brackets on both sides of this equation and we found out that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared plus A squared plus X squared minus 2 times A times X. And it is equals to B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. Here we have X squared on both sides of this equation, so X squared will get cancelled. After cancelled X squared, inside of the equation 3 we left only if A squared plus A squared, that is 2A squared minus 2AX. In the other side of the equation 3 we have B squared plus B squared, that is 2B squared plus 2XB. Here we divided this equation 3 by 3. We divided the equation 3 by 2, and finally found out that according to equation 3, 2A squared over 2 is A squared, minus 2AX over 2 is minus X, and this is equals to 2B squared over 2 is B squared, and 2XB over 2 is XB. So in total, according to equation 3, we found out that A squared minus AX equals to B squared plus XB. Here we added AX to this equation 3, and found out that according to equation 3, A squared equals to AX plus BX plus B squared. Here we subtracted B squared from this equation 3, and found out that according to equation 3, A squared minus B squared equals to, here we have BX plus AX. So we took out x, the second Riemann factor from those two expressions. So inside the brackets we left with a plus b. So according to equation 3, in total we should found out that a squared minus b squared equals to x times a plus b. Here we have the famous algebraic identity that says that a squared minus b squared equals to a plus b times a minus b. And it is equals to x times a plus b. A and b are the lengths of the big square and the small square, and therefore there must be a positive number. When you add two positive numbers to each other, the result must be a positive number. So a plus b must be a positive number. Therefore, it is allowable to divide this equation 3 by a plus b because it can never be equal to 0. It must be a positive number. So we divided this equation 3 by a plus b. So here a plus b we get cancelled, and we left this out of equation 3 with a minus b. Here also a plus b we get cancelled, and we left only with x. So in total, according to equation 3, we should find out that a minus b equals to x. Here we added b to this equation, and finally found out that a equals to x plus b. Here we subtracted x from this equation, equation 3, and finally found out that according to equation 3, a minus x equals to b. Here we squared both sides of this equation, equation 3, and finally found out that according to equation 3, a minus x squared equals to b squared. Repeat again, according to equation 3, a minus x squared equals to b squared. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of this green shape equals to the area of the big semicircle minus the area of the big square ABCD minus the area of the small square MEFC. Repeat again, the area of the green shape in total it is equals to the area of the semicircle minus the area of the big square ABCD minus the area of the small square. The area of the big semicircle must be equal to the area of the circle over 2. That is to say, it must be equal to pi r square over 2. R is 5, so pi r square is 25 pi over 2. Minus the area of the big square, one side of the big square is a, therefore the area of the big square must be equal to a square, so it is minus a square. The length of one side of the small square is b, therefore the area of the small square must be equal to b square, so it is minus b square. So in total we found out that the area of the green shape equals to 25 pi over 2 minus a square minus b square. So it is 25 pi over 2, and here we took minus 1 and second factor from those two expressions, so inside the brackets we left with a square plus b square. So in total we actually found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. According to equation 1, we have already found out that 25 equals to a square plus a minus x square. While according to equation 3, we already found out that a minus x square equals to b square. Again, according to equation 3, a minus x squared equals to b squared. Therefore, we can substitute a minus x squared in this equation 1 by b squared from equation 3. We did it, and we found out that according to equation 1, 25 equals to a squared, and a minus x squared is b squared. So in total, according to equation 1, 25 equals to a squared plus b squared equals to 25. Therefore, we can substitute a squared plus b squared here by 25. We did it, and we found out that in total, the area of the green shape equals to 25 pi over 2 minus a square plus b square, that is 25. So it is 25 pi over 2 minus 25. So in total, we found out the area that we are looking for in this question, that is the area of this green shape, it is equal to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the value of this expression is equal to 14.27 square units in its size. And repeat again, we actually found out that the area of this green shape, that is the area that we are looking for in this question, it is equal to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the area of this green shape is equal to 14.27 square units in its size. Okay, thank you very much.